Welcome to today's scientific lecture on Guinness World Records in nanoscience and nanotechnology. Over the next 15 minutes, we'll explore some of the most remarkable achievements at the nanoscale, a world where dimensions are measured in billionths of a meter. Before we dive into the records, let's establish what we mean by nanoscience. Nano comes from the Greek word meaning dwarf. 1 nanometer is 1 billionth of a meter. 1 nanometer equals 10 to the negative 9 meters, or 0.000000001 meters. To give you some perspective, a human hair is approximately 100,000 nanometers wide. A single strand of DNA is about 2 nanometers in diameter. Here's a visual comparison. The large circle represents a cross-section of a human hair at 100,000 nanometers. The tiny green rectangle is DNA at 2 nanometers. And the even smaller red rectangle represents a single atom at about 0.1 nanometers. Let's start with our first world record, the smallest movie ever made. In 2012, IBM researchers created a stop-motion film called A Boy and His Atom, which earned the Guinness World Record. This movie was created by moving individual carbon monoxide molecules on a copper surface. Each frame of the movie is only about 4.5 nanometers across. The researchers used an instrument called a scanning tunneling microscope, or STM, to precisely position each atom. This microscope can both image and manipulate individual atoms. Each white dot in this diagram represents a single carbon monoxide molecule. The STM tip, shown by the yellow arrow, can pick up and move these molecules one at a time to create different frames of the movie. You might be wondering, how does a scanning tunneling microscope work? Let me explain the quantum mechanical principle behind it. An STM works by exploiting a quantum mechanical phenomenon called electron tunneling. When a sharp metallic tip is brought extremely close to a conducting surface, electrons can tunnel through the vacuum gap. The tunneling current I is proportional to e to the negative 2 kappa d, where d is the distance between the tip and surface. This exponential dependence makes the STM incredibly sensitive to height changes. A change of just 0.1 nanometers in the tip-to-surface distance changes the tunneling current by approximately a factor of 10. This extreme sensitivity allows atomic-scale imaging and manipulation. Let's do a quick back-of-the-envelope calculation. How many atoms were moved to create this movie? The film is 242 frames long. Each frame contains roughly 100 carbon monoxide molecules that need to be positioned. So the total number of molecule movements is approximately 242 times 100, which equals 24,200 manipulations. Remember, each of these carbon monoxide molecules had to be individually picked up, moved, and placed with nanometer scale precision. The entire project took researchers several weeks to complete. Our second record involves data storage. In 2017, researchers at the Delft University of Technology created the world's smallest hard drive, storing data at the atomic level. They managed to store 1 kilobyte of data, which is 8,000 bits, in a space just 100 nanometers wide. That's about 1,000 times smaller than the width of a human hair. Each individual bit was represented by the presence or absence of a single chlorine atom on a copper surface. A chlorine atom in one position means binary 1, and in another position means binary 0. This diagram shows how binary data is encoded. Green circles represent chlorine atoms. Their presence encodes a 1, and their absence encodes a 0. This creates a binary pattern that can store information. Now let's calculate the storage density of this atomic hard drive and compare it to conventional technology. Each bit occupies approximately 0.3 nanometers squared, which equals 0.09 square nanometers. The density is 1 bit divided by 0.09 square nanometers, which gives us approximately 11 bits per square nanometer. To convert this to more familiar units, we multiply by the conversion factor. This gives us about 7 times 10 to the 15 bits per square inch, or roughly 1,000 terabytes per square inch. For comparison, modern commercial hard drives achieve about 1 to 2 terabytes per square inch. This atomic storage is roughly 1,000 times denser than current technology. You might be asking, if this technology is so impressive, why aren't we using it in our computers right now? There are several practical challenges. First, this technology requires ultra-high vacuum conditions. The atoms would immediately react with oxygen or water molecules in normal air, destroying the data. Second, the system must be kept at extremely low temperatures, typically around -260 degrees Celsius, to prevent thermal motion from disrupting the atomic positions. Third, the read and write speeds are incredibly slow compared to modern electronics. Moving individual atoms takes much longer than flipping electronic bits. Finally, scaling this up to practical sizes with the necessary infrastructure is currently beyond our technological capabilities and would be prohibitively expensive. Our third record involves DNA nanotechnology. In 2018, researchers at the California Institute of Technology created the world's smallest origami bird, constructed entirely from DNA molecules. This achievement uses a technique called DNA origami, where long single strands of DNA are folded into predetermined shapes using shorter DNA strands called staples. The green line represents a long scaffold strand of DNA. The blue lines are short staple strands that bind to specific sequences on the scaffold, forcing it to fold into a predetermined three-dimensional shape. The resulting origami bird measures approximately 150 nanometers from wingtip to wingtip. That's about 1/500th the width of a human hair. The fundamental principle behind DNA origami is Watson-Crick base pairing. DNA consists of 4 bases: adenine, thymine, guanine, and cytosine. Adenine always pairs with thymine, and guanine always pairs with cytosine. This complementary base pairing is what allows DNA origami to work with such precision. Each base pair in the DNA double helix is approximately 0.34 nanometers long. The helix makes a complete turn every 10.5 base pairs, or about 3.4 nanometers. Let's estimate how many DNA base pairs are needed to construct this tiny origami bird. A typical DNA origami structure uses a scaffold strand of about 7,000 nucleotides long. This is often derived from the genome of a bacteriophage called M13. To fold this scaffold into the bird shape, you need approximately 200 different staple strands, each about 20 to 30 nucleotides long. So the total number of nucleotides in the complete structure is approximately 7,000 plus 200 times 25, which equals about 12,000 nucleotides. The entire structure is held together purely by hydrogen bonds between complementary base pairs. Each adenine-thymine pair has 2 hydrogen bonds, and each guanine-cytosine pair has 3 hydrogen bonds. Our fourth record is from the first ever Nanocar race held in 2017 in Toulouse, France. Teams from around the world competed to build the fastest molecule-sized car. The winning Nanocar, built by a team from Austria, traveled at a blistering 95 nanometers per hour. Now that might not sound fast, but at the molecular scale, it's quite impressive. This diagram shows the basic structure of a nanocar. The 4 white circles represent fullerene wheels, which are spherical carbon molecules. The green rectangle is the molecular chassis, and the blue structure is a light-activated motor unit. These nanocars were powered by electric pulses from scanning tunneling microscope tips. The STM tip provides energy that causes the molecular motors to rotate, propelling the car forward. Let's put this speed of 95 nanometers per hour into perspective with some calculations. 95 nanometers per hour equals 9.5 times 10 to the negative 8 meters per hour. The nanocar itself is approximately 4 nanometers long. So the car travels about 95 divided by 4, which equals approximately 24 body lengths per hour. That's roughly 1 body length every 2.5 minutes. How does this compare to a real car? Let's make an analogy. A typical car is about 4 meters long and travels at 100 kilometers per hour on the highway. That's 100,000 meters divided by 4 meters, which equals 25,000 body lengths per hour. Comparing these, the nanocar is about 1,000 times slower relative to its body length. But remember, it's operating at the molecular scale where friction and thermal noise are huge challenges. Our fifth record involves graphene, a wonder material consisting of a single layer of carbon atoms. In 2015, researchers at Columbia University created the world's thinnest light bulb using graphene. Graphene is just 1 atom thick, measuring only 0.335 nanometers. It's the thinnest material known to science, yet it's incredibly strong and conducts electricity extremely well. This shows the hexagonal lattice structure of graphene. Each white circle represents a carbon atom. The atoms are arranged in a perfect honeycomb pattern, which gives graphene its remarkable properties. When electrical current passes through graphene, it heats up to over 2,500 degrees Celsius. At this temperature, it begins to emit visible light, creating the world's thinnest light bulb. Let's use the Stefan-Boltzmann law to estimate the power radiated by this graphene light bulb. The Stefan-Boltzmann law states that power equals sigma times area times temperature to the fourth power, where sigma is the Stefan-Boltzmann constant. Sigma equals 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the fourth power. Let's say the temperature is 2800 Kelvin, and the graphene sheet is 10 micrometers by 10 micrometers, giving an area of 10 to the negative 10 square meters. Plugging in these values, the power is approximately 3.5 milliwatts. That's a tiny amount of light, but visible to the human eye in a dark room. Graphene also holds the record for the strongest material ever tested. Its strength-to-weight ratio is truly extraordinary. Graphene has a tensile strength of 130 gigapascals. That means it can withstand enormous forces before breaking, despite being just one atom thick. 130 gigapascals equals 1.3 times 10 to the 11 pascals. To put this in perspective, a hammock made of graphene with the same weight as a cat could theoretically support an elephant without breaking. That's about 4,000 kilograms supported by 4 kilograms of material. Why is graphene so incredibly strong? It comes down to the carbon-carbon bonds. Each carbon atom in graphene forms 3 covalent bonds with its neighbors. These carbon-carbon bonds have a length of 0.142 nanometers and are among the strongest chemical bonds in nature. Each carbon-carbon bond in graphene has an energy of approximately 5.5 electron volts, which equals 8.8 times 10 to the negative 19 joules. Additionally, the two-dimensional hexagonal lattice structure distributes stress evenly across all bonds, preventing weak points that would cause failure in three-dimensional materials. Our seventh record is crucial for the future of computing, the smallest transistor ever made. In 2016, Lawrence Berkeley National Laboratory created a transistor with a gate length of just 1 nanometer. Transistors are the fundamental building blocks of all modern electronics. They act as switches that control the flow of electrical current, enabling all digital computation. This diagram shows a simplified transistor structure. The gray rectangle is the silicon substrate. The blue regions are the source and drain. The golden vertical structure is the gate, which is only 1 nanometer wide. Modern computer processors contain billions of these transistors. For example, Apple's M1 chip contains about 16 billion transistors in an area smaller than a postage stamp. At 1 nanometer, we face a significant challenge: quantum tunneling. When dimensions get this small, electrons can tunnel through barriers they classically shouldn't be able to cross. The tunneling probability follows an exponential relationship with the barrier width. As the gate gets smaller, unwanted tunneling increases, causing current leakage even when the transistor should be off. This quantum mechanical effect creates a fundamental physical limit to how much smaller we can make transistors using conventional silicon technology. We're approaching the atomic scale limits of Moore's law. Our eighth record involves nanotechnology in surface engineering. Researchers have created superhydrophobic surfaces with contact angles exceeding 170 degrees. This technology is inspired by nature, specifically the lotus leaf. Lotus leaves stay remarkably clean because water droplets roll off, taking dirt with them. This is called the lotus effect. The surface is covered with nanoscale pillars that create tiny air pockets. When a water droplet, shown in blue, sits on this surface, it rests mostly on air rather than the solid material, creating an extremely high contact angle. This technology has numerous applications: self-cleaning windows and solar panels, anti-icing coatings for aircraft, waterproof electronics, and stain-resistant fabrics. Let's calculate the adhesion force between a water droplet and this superhydrophobic surface. The adhesion force equals the surface tension gamma times the perimeter of the droplet times 1 plus cosine theta, where theta is the contact angle. The surface tension of water is 0.072 newtons per meter at room temperature. with a contact angle of 170 degrees and a droplet radius of 2 millimeters. The adhesion force is approximately 10 micronewtons. This is incredibly small, which is why water droplets roll off so easily with just the slightest tilt. Our ninth record is Vantablack, one of the darkest substances known to science. It absorbs 99.965% of visible light. Vantablack consists of vertically aligned carbon nanotube arrays. These nanotubes are like microscopic forests of hollow carbon cylinders, each about 20 nanometers in diameter and tens of micrometers tall. When light enters this nanotube forest, it bounces between the tubes multiple times. Each bounce absorbs some energy, and very little light escapes back out, making the material appear extremely black. Vantablack has important applications in astronomy, where it's used to reduce stray light in telescopes. It's also used in sensors and optical equipment, where minimizing reflections is critical. Let's calculate how much light energy is absorbed by Vantablack compared to ordinary black paint. Vantablack absorbs 99.965% of incident light, reflecting only 0.035%. Ordinary black paint absorbs about 97%, reflecting about 3%. The ratio of reflected light is 3 divided by 0.035, which is approximately 86. So Vantablack reflects about 86 times less light than ordinary black paint. Our 10th record combines topology with nanotechnology. Researchers created the smallest Möbius strip, a twisted loop with only one surface, using DNA origami. A Möbius strip is a fascinating topological object. If you take a strip of paper, give it a half twist, and connect the ends, you create a surface that has only one side and one edge. This DNA Möbius strip is formed by designing a DNA double helix that curves back on itself with a 180-degree twist. The green loop represents the overall structure, with the twist indicated by the crossing line. This molecular Möbius strip has a diameter of approximately 50 nanometers. It's constructed using DNA origami techniques with carefully designed sequences that force the twist. Creating such structures helps scientists understand how topology affects molecular properties and could lead to new types of nanomachines and sensors that exploit topological features. Our final record involves molecular switches that can change state in femtoseconds. 1 femtosecond is 1 quadrillionth of a second. 1 femtosecond equals 10 to the negative 15 seconds. To put this in perspective, light travels only about 0.3 micrometers in 1 femtosecond. These ultra-fast switches work through photoisomerization, where a molecule changes its shape when hit by a photon of light. The most famous example is the molecule azobenzene. The green circle shows the trans configuration of azobenzene. When light hits it, it switches to the cis configuration shown in red in less than 100 femtoseconds. The bent shape of the cis form is indicated by the angled line. Such fast molecular switches could enable optical computers that operate at speeds thousands of times faster than current electronic computers and ultra-high-speed data storage systems. Let's calculate how many times such a molecular switch could theoretically change state in 1 second. If the switching time is 100 femtoseconds, that's 10 to the negative 13 seconds. The number of switches per second equals 1 divided by 10 to the negative 13, which is 10 to the 13, or 10 trillion switches per second. Compare this to a modern CPU running at 5 gigahertz, which is 5 times 10 to the 9th cycles per second. The molecular switch is about 2,000 times faster. Let's summarize what we've learned today about these remarkable Guinness World Records in nanoscience and nanotechnology. We've explored an incredible range of achievements, from IBM's atomic movie to femtosecond molecular switches, from DNA origami birds to 1 nanometer transistors. A common theme throughout these records is achieving unprecedented precision and control at the atomic and molecular scale. We can now manipulate individual atoms and molecules with remarkable accuracy. The main challenges moving forward include dealing with quantum mechanical effects that dominate at these scales, scaling up these techniques for practical applications, and maintaining control under real-world conditions. Looking to the future, what might the next generation of records look like? Let me speculate on a few possibilities. We might see truly quantum computers with thousands of stable qubits, molecular assemblers that can build complex structures atom by atom, or room-temperature superconducting nanowires. These advances could revolutionize medicine with targeted drug delivery at the cellular level, create ultra-efficient solar cells and batteries, or enable quantum sensors that can detect single molecules. It's important to recognize that we're approaching fundamental physical limits imposed by quantum mechanics, thermodynamics, and the atomic structure of matter. The Heisenberg uncertainty principle tells us that delta x times delta p is greater than or equal to h bar over 2. This places a fundamental limit on how precisely we can control particle positions and momenta simultaneously. At room temperature, thermal energy is about 26 millielectron volts. This random thermal motion makes it difficult to maintain precise nanoscale structures and poses challenges for room temperature nano devices. Nanoscience and nanotechnology will play crucial roles in addressing some of humanity's greatest challenges. In energy, we're developing more efficient solar cells using quantum dots, better batteries with nanostructured electrodes, and improved materials for hydrogen storage using carbon nanotubes. In medicine, nanoparticles can deliver drugs directly to cancer cells. Nanosensors can detect diseases earlier, and nanomaterials are enabling better tissue engineering and regenerative medicine. For the environment, nanomaterials are improving water purification through advanced membranes, enabling better sensors for pollution detection, and helping develop more efficient carbon capture technologies. In computing, as we reach the limits of conventional silicon transistors, nanotechnology offers new pathways like carbon nanotube transistors, spintronics, and quantum computing architectures. As we conclude this lecture, I want you to appreciate the incredible achievement represented by each of these world records. Each record represents years of research, overcoming immense technical challenges, and pushing the boundaries of human knowledge and capability at the smallest scales we can access. These achievements require collaboration across physics, chemistry, biology, materials, science, and engineering. No single discipline can tackle these challenges alone. The nanoscale is a fascinating regime where quantum mechanical effects meet classical physics, where individual atoms matter, and where we can engineer properties that don't exist in bulk materials. Let me leave you with one final calculation about the scale of impact these technologies could have. The global nanotechnology market in 2020 was approximately $1.8 trillion. Projections suggest it could reach $33 trillion by 2030. This represents enormous potential for economic impact and technological advancement. Thank you for joining me on this journey through the fascinating world of nanoscience and nanotechnology. The records we've discussed today are just the beginning of what promises to be an exciting century of discovery at the nanoscale.